5.4 Trapezoids and Kites in Unit 5 Polygons. Let's finish up this video.
Okay then, if all the quadrilaterals we've seen so far are examples of parallelograms, what's an example that's not a parallelogram? Well, to see one, let's start over with our square again. But this time, we're going to change it by moving just one of its vertices, like so. Now, one of the pairs of sides is still parallel, but the other is not. And a quadrilateral that has only one pair of parallel sides is called a trapezoid. Well, actually, this is where classifying quadrilaterals gets a little messy. And that's because this sort of shape is called a trapezoid in America, but it's called a trapezium in other countries, like the UK. Trapezoid, trapezium, trapezoid, trapezium. It's a trapezoid! At least they both start with the word trap, so it's not too confusing. Yet. Okay, so this quadrilateral is a trapezoid, or trapezium, because it has only one pair of parallel sides, and the other sides are not parallel. Here are a couple more examples of quadrilaterals that have only one set of parallel sides. All right then, what about quadrilaterals that have no parallel sides at all, like this one? These opposite sides are not parallel, and these opposite sides aren't parallel either. So what do we call this kind of polygon? Now here's the really confusing part. In America, this is sometimes called a trapezium. But isn't that what they call a quadrilateral with only one pair of parallel sides in the UK? Yep. Unfortunately, the same word is used to describe two different things in two different countries. Trapezium, 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 trapezium. Well, at least they both like football. But to keep things clear at Math Antics, we're not going to call a quadrilateral that has no parallel sides a trapezium. We don't think it needs a special name. So we're just going to call it a quadrilateral. So to summarize, any polygon that has exactly four sides is called a quadrilateral. And if it has no parallel sides, we still just call it a quadrilateral. But if it has one and only one pair of parallel sides, we call it a trapezoid or a trapezium. Or if it has two pairs of parallel sides, we call it a parallelogram. And you've already seen that there's several types of parallelograms called rectangles, rhombuses, and squares. All right, so that's the basics of classifying quadrilaterals. There's a few other special types of quadrilaterals, but we've learned the most important ones. But there is one more really important thing you need to know about quadrilaterals. You need to know that the sum of the angles of a quadrilateral is always 360 degrees. Now that's pretty obvious for a square or a rectangle. Those shapes have four right angles. And since we know that a right angle is 90 degrees, 4 times 90 gives us 360. But to see that it's also true for any quadrilateral, let's have a look at these 4 different examples. Watch what happens when we draw a line on each of them between a pair of opposite vertices. Each of the quadrilaterals got divided into 2 triangles. In the triangles video, we learned that the sum of the angles of a triangle is always 180 degrees. So it's not too hard to see that since the angles of a quadrilateral form 2 triangles, the sum of those angles would be 2 times 180 degrees, which is 360. Knowing that the angles of a quadrilateral add up to 360 degrees can help you solve problems like this one. For this quadrilateral, we're told what 3 of the angles are, but the 4th one is unknown. To find the unknown angle, all we have to do is add up the 3 angles that we do know, and then we subtract that from the total, which we now know is 360 degrees. So 100 plus 80 plus 60 equals 240. And then 360 minus 240 equals 120. So the unknown angle is 120 degrees. Let's look at one more unknown angle problem that's a little tricky. This problem asks us to find the unknown angle A in a parallelogram. But it looks like they only told us what one of the angles is, and the other 3 are unknown. So how can we possibly figure this one out? solve this problem, we need to know an important fact about parallelograms. Because parallelograms are always made from pairs of parallel sides, that means they also form pairs of equal angles. It's the opposite angles that form these pairs. For example, in this parallelogram, the angles A and C are equal because they're on opposite corners, and the angles B and D are equal because they're on opposite corners. Now remember, this is only true for parallelograms. This won't work for things like trapezoids. So in our problem, even though we're only given the measure of one angle, since we know it's a parallelogram, that's all we need to figure out all the other angles. First of all, we know that angle B must also be 50 degrees because these opposite angles must be equal. Next, we know that the other two angles, A and C, must also be equal. So if we can figure out how many degrees are left over, or still unknown, we can just divide that amount equally between A and C. Well, the total of all the angles is 360. So if we subtract the angles that we know, 50 plus 50 equals 100, and 360 minus 100 equals 260, we know that A and C must each be half of 260 degrees, and 260 divided by 2 is 130, so angle A must be 130 degrees. Okay, that's all for this video. We've learned the basics of how to classify quadrilaterals, and we learned that a quadrilateral's angles add up to 360 degrees. Remember, getting good at math takes practice, so be sure to work the exercises for this section. As always, thanks for watching Math Antics, and I'll see you next time.
Okay, so you've just learned that a trapezoid is a quadrilateral with exactly one pair of parallel sides. The parallel sides are always called the bases, even if the quadrilateral, or in this case trapezoid, is turned on its side. A trapezoid has two pairs of base angles, the top and the bottom, or if it's turned on its side, the left and the right side. For example, in this trapezoid ABCD, A and D are base angles because they are consecutive at a base, and B and C are base angles because they are consecutive at a base. The non-parallel sides of your trapezoid are called the legs of the trapezoid. If you want to determine if something is a trapezoid or not, you need to determine if it has one pair of parallel sides. So look at ORST here. It is a quadrilateral graphed on the coordinate plane, and it wants us to show that it's a trapezoid. So we need to show that either RS is parallel to OT, or we need to show that OR is parallel to ST. So I think we can look at this and determine that RS and OT appear to be the two sides that are parallel to each other, the two sides that would never intersect each other. A quick reminder of the slope formula, y2 minus y1 over x2 minus x1. And if we want to find the slope of RS, we can use that formula, y minus y, or 4 minus 3 over 2 minus 0, simplifying to 1/2. Or we can count rise over run 1 over 2. Then we find the slope of OT, the side we suspect is parallel to it, and we do y minus y, or 2 minus 0, over x minus x, or 4 minus 0, which simplifies to 2/4 or 1/2. Or we can count rise over run 1, up 1 over 2, up 1 over 2, or we can say up 2 over 4, 2 over 4 reduces to 1 over 1/2. Regardless, we now see that the slope of RS and the slope of OT match each other. And when two lines have the same slope, we know that they're parallel with each other. Then we're going to look at the slopes of RS and OT. And we want to make sure that they're actually, sorry, not RS and OT, ST and OR. We want to make sure that those are not parallel because we only want one side of parallel lines. And so we look at OR first, or ST first, and we see it's going to have a negative slope because it's decreasing here. And we have 2 minus 4 over 4 minus 2, which gives us a slope of -1. And if we look at OR, We have 3 minus 0 over 0 minus 0, which is undefined. These two are not parallel to each other. And so we do have one side of parallel lines, or parallel sides, meaning that this has to be a trapezoid. Isosceles trapezoids are just like isosceles triangles. So what you have is the legs of the trapezoid will be congruent to each other. So we'll say that again. If the legs of a trapezoid are congruent to each other, if they're the same measure, then the trapezoid is going to be an isosceles trapezoid. Some theorems to follow up. If a trapezoid is isosceles, then each pair of base angles is congruent. If a trapezoid has a pair of congruent base angles, then it's an isosceles trapezoid. So if all we're given are those base angles being congruent, that's enough to say that it's a trapezoid, isosceles trapezoid. A trapezoid is isosceles if and only if its diagonals are congruent. So this tells us that if we're looking at a trapezoid and the diagonals are the same measure, then it has to be isosceles. Or if we're given an isosceles trapezoid, then we know the diagonals have to be congruent or the same measure. So let's take a look at this picture here. It says the stone from the arch in the diagram is an isosceles trapezoid. Find the measure of K, M, and J. So here's my isosceles trapezoid. Here are my parallel sides J, M, and K, L, making base angles K and L, base angles J and M. We are told in the prompt that this is an isosceles trapezoid, meaning that the base angles have to be equal to each other. So that means K and L have to be the same measure. Okay, so that tells us that K has to be 85 degrees. In the video, he talked about the fact that the sum of an isosceles trapezoid has to be 360 degrees. That's going to help us determine J and M. J and M do have to be the same measure because it's an isosceles trapezoid. So here's what we have. Because L and M are consecutive interior angles, they are supplementary. So we can find them by saying, okay, L and M are supplementary. 180 minus 85 gives us 95, which is this one right here. And then we can find J because these have to be the same. So when we're looking at this, there is an alternate way we can solve for this like he did in the video. So I want to show you that as well. So here's kind of what it took you through here. K and L have to be the same measure because it's isosceles. So that means K has to be 85 degrees. And then J and M have to also be the same measure. And so what we can do is we can say, okay, if we know that K, L, M, and N, the sum of the interior angles has to be 360, then we can take that 360 degree total, subtract away angle K, and subtract away angle L. So if we take 360 and we subtract 85, and we subtract 85 again, that gives us 190 left over. So I can take this leftover 190 degrees that's being split between these two and divide it by 2. So I can take 190, divide that by 2, and that's going to give me 95 degrees. So each one of these, J and M, has to be 95 degrees in order for the sum of it to equal 360. So that's sort of two ways to think about it. You can think about the fact that these two have to be supplementary with each other, or you can think about the fact that the entire quadrilateral has to add to be 360. All right, the next shape we're going to be looking at is a kite. He did not talk about the kite in his video, but it is a pretty normal quadrilateral, so we're going to go ahead and cover it now. A kite is a quadrilateral that has two pairs of consecutive congruent sides. Remember, consecutive means they happen one right after the next. So I could trace it without picking up my pencil. Here and then here. These would be consecutive, and they would have to be congruent for this to be a kite. And then I have another pair. Remember, I should be able to trace without picking up my pencil. Wow, that was terrible. And these two have to be congruent with each other. Okay? In a kite, you have perpendicular diagonals. In a kite, you have perpendicular diagonals, meaning the diagonals will meet at a 90-degree angle. The other theorem that goes with your kite is it's going to have exactly one pair of opposite angles that are congruent. Exactly one pair. So generally, it's going to be these two bigger obtuse angles. Like that's the way you would typically see it, but we could squeeze this together, or not squeeze together, but yeah, like push B and D towards each other and start narrowing them. And that would, I could shrink it and it would kind of look crazy. But anyways, so exactly one pair of opposite angles that are congruent. All right, let's see if we can use this. Find the measure of angle D in the kite shown to the right. So you can see that it's a kite because DE and EF are consecutive sides and they're congruent. DG and GF are consecutive sides and they're congruent. So that's kind of what tells you that it's a kite. It tells us that the measure of angle E is 124 and the measure of angle G is 180, and it wants us to find the measure of angle D, which is this guy over here. Now, remember, it's a kite, so I've got to have one pair of congruent sides. Obviously, that pair of congruent sides can't be E and G because one's 124 and one's 80. So that kind of tells us that D and F have to be the same measure. Okay, so if D and F are the same measure, and this is a quadrilateral, sum of the angles is 360, that's going to help us determine what's this measure. So we're going to say that the measure of angle D plus the measure of angle F plus 124 plus 80 has to be 360 degrees. That's 360 is the sum of the interior angles of a quadrilateral. Remember that D and F are the same measure. So if I were working this on the board with you, I probably would have just called the measure of angle D X, right? Because we like that better. So that means that 2x, or two measures of angle D, plus 204 has to be 360. So this is the same thing that we did on the previous example, where you take 360, subtract what you know, divide it in two, and split it amongst the two congruent angles. So 360 minus 204, and then divide by 2, and you're going to get that the measure of angle D has to be 78 degrees. A quick top-down flow chart of your quadrilaterals. So remember, I'm using this word quite a lot. A quadrilateral is just a four-sided closed figure. Then we can organize quadrilaterals in three ways. Quadrilaterals that have two pairs of parallel sides, or opposite parallel sides. Our second organization from there would be one pair of parallel sides. So parallelograms have two pairs of parallel sides. Trapezoids have one pair of parallel sides. And then you've got no parallel sides, like the kite. But you can actually organize further than that. So if we look at our trapezoid, we can organize it even more and find an isosceles trapezoid where we've got congruent legs and congruent base angles. With our quadrilaterals, we can organize our parallelograms a little further, so we can say, okay, what happens if it's equilateral? What happens if it's equiangular? What happens if it's equilateral and equiangular? So remember, equilateral is your rectangle. Equiangular is your rectangle, 4 right angles. Equilateral is your rhombus. And then where rectangle and rhombus meet would be the square. All four sides are congruent, all four angles are congruent. Quadrilateral ABCD has at least one pair of opposite angles that are congruent. What type of quadrilateral meet this condition? So stop right here and think for just a second. How many quadrilaterals have I talked about where at least one pair of opposite angles are congruent? Because there's a lot. And you might even think about pausing the video really quick and jotting down some thoughts on how many different quadrilaterals meet that condition. So think about that. Opposite congruent angles, how many of these have opposite congruent angles? Not all of them, but quite a few of them. Parallelograms, rhombuses, rectangles, squares, kites, all of these have opposite angles that are congruent. What is the most specific name for the quadrilateral ABCD? So the only information we're given is that the diagonals bisect each other. We're not told anything about the angles, even though our eyes might tell us they look right. We're not told anything about the side lengths, even though our eyes might tell us they look the same. We have to be careful here, because if the only thing I'm given is that what is true about the diagonals, then all I can say is that it's a parallelogram. Anything else would be assuming the sides are the same, or assuming the angles are right when I'm not told that information. So the answer in this case would be a square. Okay, time to practice. There's an assignment following this practice. Good luck. I hope this helps.